Hi, welcome to Math372, Lecture 21. Now that it is post-Halloween, there will almost surely be candy for the rest of the semester, as we have a lot of candy left over in the house. Not responsible for any and all food poisonings, not responsible for any and all nut allergies. You are eating the candy at your own risk. At most, 1% was deliberately poisoned. Okay, so what I want to do is I want to basically turn today into Improv Wednesday. So I want to talk about the Riemann Zeta function. I want to talk about the gamma function. I don't have too much of a planned agenda. There are certain things I want to get to, but if there are things you find interesting, I'm happy to go down that route and explore. I also want to pose a problem in terms of Stirling's formula, which estimates n factorial, which is related to the gamma function. If you can find a way to make this argument work, I don't know if anybody has ever done so. I'd like to see that. And I will convert that to grade for the course, homework exemptions, whatnot. The other thing is, for those of you who are not seniors, homework exemptions can be propagated from course to course. I am teaching Calc 3 in the spring. If you need to use it in Calc 3, you have trouble, as this is a prereq for this class. All right. Do you want to start with the integration summation preliminaries, or do you want to start with the Riemann Zeta function?
Preliminaries.
Preliminaries. OK. So we need what's called partial summation. How many of you have seen partial summation before? OK. This is one of the bread and butter tools of the number theorists. Now, there are a lot of different versions of partial summation. There's the discrete version, and there's the integral version. I prefer the integral version typically. And what we'll have is we'll have a sum n, maybe it goes from 1 to big N of an h of n, where h is some nice function. And this will equal a of n, h of n, minus the integral from 1 to n of a of x, h prime of x, dx, where a of x is the sum, little n, up to x of an. There is a small chance I have shifted my indices here by 1. I'm not that worried about that. I might have shifted the index here by 1. I'm not that worried about that. We'll try to prove it right now, and then hopefully figure out exactly what the right variant of this is. The main thing is typically we will do this with functions such that maybe a of n is bounded, and h of n is going to 0, so that this boundary term won't matter. So if I've shifted my index off, not going to matter. The point of something like this is if the sum of the little an's is bounded, and h is such that its derivative is decaying faster than h, then this buys us some convergence. So the whole point of this will be to go from a sum that doesn't really converge well to something that converges better. Notice how this is essentially smoothing things out. And so if the sequence an is fairly nice and regular, I might have really good understanding of a of x, main term plus a small error term. And I can then have a good chance of controlling something like this. Does this remind you of anything you've seen before?
So integration.
Yeah, it looks a lot like integration by proxy. The integral of u of x dv of x, or I think you often write it as maybe v prime of x dx. Either way is fine. From 1 to n would be u of x v of x at 1 and n minus the integral from 1 to n of u prime of x v of x dx. So essentially, this is a discrete version of that. We can't just immediately claim that we have this because we're assuming we have differentiable functions here, and these are step functions. So let's try to just talk a little bit about why this should be true. So proof sketch. Let's look at the function a of x, h prime of x. Now, the nicest function to integrate is just the derivative of any function. I can integrate h prime of x very easily. I can integrate anything prime very easily. The problem is I have this a of x here. Well, a of x is mostly constant, right? A of x only changes at basically, set of measures 0 whenever x passes through an integer. So what I can do is I can look at the integral from 1 to n of a of x, h prime of x, dx. And I can write this as an integral from 1 to 2 of a of x, h prime of x dx, plus an integral from 2 to 3 of a of x, h prime of x dx, plus an integral from 3 to 4 of a of x, h prime of x dx, and so on and so on and so on. So in this region, what will a of x be? It'll just be a1. So what we'll get is we'll get a1, and then we integrate h prime. So we'll just get h of x. We'll get h of 2 minus h of 1. For the next term, what's a of x going to be in this region? a1 plus a2. So we'll get a1 plus a2, and now we'll get h of 3 minus h of 2. And then the next one we'll get plus a1 plus a2 plus a3, h of 4 minus h of 3, plus dot, 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 dot. And now all we need to do is we just need to group terms. I've got a minus h2, I have a plus h2. The a1s cancel. And I'm left with a minus a2. Are we worried that there's a minus a2? No, we've got a minus integral of a of x. So the minus will go away. So this will give us, we'll have a minus a1 h1, a minus a2 h2. Let's look at the h3 term. We'll have an a1 a2 h3. We'll have a minus a1 a2 a3. So we'll have a minus a3 h3. Minus dot, dot, dot. So at this point, the proof is hopefully clear. It then just all comes down to we've got to just make sure that the boundary term is matching perfectly, and that's where we throw in this little a n h of n at the very end. So if you want a nice exercise, just write this up cleanly. This is close to cleanly. In a graduate level class, this is more than enough. But you want to just make sure you can go through this. All right, so then the question becomes, when would we like to use a sequence like this? Why is this so useful? So by training, I'm a number theorist. And one of our default go-to methods is partial summation. It allows you to pass from a sum that you know to a sum that you might prefer to understand later. So one of the things I want to try to teach you today is that in mathematics, small amounts of discrimination are OK. Large amounts, no, but small amounts are. You should not treat all primes equally. Now, what does this mean? It means if I'm studying primes from 1 to x, the primes are more numerous in the beginning, and then they get a little bit sparser and sparser and sparser further out. And what we're going to do is we're going to rescale the primes a little bit based on their size. And that's going to make counting them a lot easier. So how many of you have seen before using like a log p weight with primes? Okay, I'm seeing some heads going yes, not just mine, because I can actually see myself in the video. Okay? I'm just being honest. Have you seen why we weight primes by log p? Or is that just mysterious that they just tell you weight the primes by log p? All right, so one of the things I want to try to show you is why we care about these log p weights. Okay, so this is the preliminary that we need. I will try to keep this on the board as long as possible. So I want to start talking about the Riemann Zeta-Function. So we're doing now, I think it's chapter 6. This is the gamma function and the Riemann Zeta-Function. These are two of the most important functions in number theory and mathematics. All right, so the Riemann Zeta-Function. So remember how we're doing the battle between Cauchy and Riemann? Riemann gets a huge credit for this one. All right, so zeta of s is defined as the sum, and goes from 1 to infinity, of 1 over n to the s. And if you go back to Calc 3, and if you forget that, just take my class, I guess, in the spring. When does the series converge? Yep. Normally in Calc 3, we would just do s as real. But we would see that, well, look, we could take absolute values. And so all that really matters is the real part of s greater than 1, it will converge. Or it will converge absolutely. if the real part of S is less than 1, but S has an imaginary part, there's a chance it could converge because we have a lot of oscillation. So we're now getting into a really delicate subject. If you have basically a main term and everything else is so small that you can afford to just shove in absolute values, the analysis is very crude. It's often very easy to do. If you have to exploit oscillation, if you have to exploit cancellation, it is significantly harder. And the techniques to handle that are more advanced. So this defines a nice holomorphic function if the real part of S is greater than 1. As S goes down to 1, what do you think happens? Do you think this converges as the real part of S goes to 1? Or do you think it diverges? So it diverges. So if I just take S equals 1, what series is this? It's the harmonic series. So there should be at least a pole, hopefully not an essential singularity, at S equals 1. Anybody know it's 2017, right? What's the next year? 2018 next year? Next year? 2020? Okay. There is really not that much mystery in the distribution of integers. We've understood the distribution of integers for a long time. So you can prove, I don't know, Dumbbell's theory of integers in arithmetic progression. There are infinitely many. You can prove there are infinitely many integers differing by 2. And, whatever you want along these lines, these are not hard proofs. How about primes? 2017 is a prime. Anybody who's doing a math competition, if you're doing the Putnam, you should know 2017 is prime. What's the next prime after 2017? Pause. And the next prime after that, more pause. Okay? The idea is we want to pass from knowledge over integers to knowledge over primes. And this is why the Riemann zeta function is so great. This is the same as the product over p prime 1 minus 1 over p to the s inverse. And this is why we care so much about this function. So the function was studied before Riemann. I don't think it was really looked at as a complex variable. We now call this the Euler Product. This should give you some idea of who was looking at this. So what does this product remind you of? Geometric series. So a really good exercise. It's essentially the fundamental theorem of algebra. Is that the two sides are the same. And so what you can do is you can look at a product over all primes less than or equal to some big P of 1 minus 1 over p to the s inverse. And then I'll expand this out, and I will have a product over all primes less than or equal to p, 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the 3s plus dot dot dot. And then I'll yes?
That's a product, not a prime.
That is a product, yes. Yes. So we use this to represent product, just like we use a sigma to represent sum. So think of this as I do this with 2, then I do it with 3, then I do it with 5, then I do it with 7. And I only have a finite product. And I expand everything out. So when I expand it out, I'm going to get a sum over n of things of the form 1 over n to the s. Now, which n will I get? Do I get every integer? I get all n whose prime factors are at most p. P divides n implies p is less than or equal to p. If you have a prime factor that's greater than p, you're not in any of these terms. And by unique factorization, no two terms, when I multiply out, are going to get to the same number. So this will tell you that this will give you a subset of that. Okay? Is this clear?
When you multiplied that out,
So think of it as 1 plus 1 over 2 to the s plus 1 over 2 to the 2s plus 1 over 2 to the 3s. And then I have the same thing with 3's, 1 plus 1 over 3 to the s. So when I start multiplying things out, I get 1, and I get 1 over 2 to the s plus 1 over 3 to the s plus 1 over 5 to the s, plus 1 over 7 to the s. And now this is 2 to the 2s. That's the same as 4. So I get a plus 1 over 4 to the s. And then I'll have the next one would be 4 times 3 would be plus 1 over 12 to the s. And when I multiply this out, I only have finitely many terms in my product. I'm never going to get, I choose something from the first, something from the second, something from the third. I can never have two different choices giving me the same number by the fundamental theorem of arithmetic. Oh, I wrote algebra. Sorry, it's arithmetic. Sorry. Algebra is later today, if we get to it. No two choices will land at the same number because every integer n has a unique prime product. When we write the primes in increasing order. So however many powers of 2, I take that one. However many powers of 3, I take that one. However many powers of 5, I take that one. And you can then see if you take the limit, as you take all the products, you're going to get the numbers 1 over n to the s. Every number will be hit, and it will be hit exactly once. So you can spend a little bit more time and make this a little bit more rigorous. But if I take finitely many products, it's not so bad. What does it mean if I take infinitely many products? The rule we have is if you have infinitely many products, you have to take one infinitely many times, and you take non-one only finitely many times. So if you just try to do the entire infinite product all at once, what you would see is, well, I can only take finitely many choices that aren't 1. If I were to take infinitely many things that aren't 1, what would that product actually be? It would be 0. Because all these numbers are going to 0. And if I take infinitely many numbers, the product would be smaller and smaller and smaller and smaller. So one way you can do this is you can take large finite products, and then you can see, well, what's the difference between this series and the sum of 1 over n to the s? Well, clearly I'm going to have every number up to p. So if I look at the difference, it would only be the sum of 1 over n to the s. It would be dominated by the sum of 1 over n to the s for n greater than p. And then because the sum converges, I can make this arbitrarily small. So if I just take more and more products, so if I look at the difference, so 1 over the sum of n goes from 1 to infinity of 1 over n to the s minus the product p less than equal to big P, 1 minus 1 over p to the s inverse. This will be less than equal to the sum n greater than p, 1 over n to the absolute value of s. Well, let's do real part of s. Real part of s. Real part of s. So by doing this, I have no oscillation. And I know, look, there's no term in this product that's not in the sum. And I have all the terms clearly up to at least big P. So I can bound this. And because the sum converges, this is the tail of a convergent series. It's going to go to 0. So as I let big P go to infinity, this has to go to that. And that's the Euler product formula. So this is called the Euler product. We will get to the Riemann hypothesis later. It is possible in principle to prove the Riemann hypothesis without using the Euler product. I would be shocked if that can happen, and I've been out long enough that I'm allowed to express shock publicly. There are functions that are very similar to the Riemann zeta function that do not satisfy the Riemann hypothesis. They don't have an Euler product. We believe fundamentally the Euler product is essential in any understanding of the Riemann zeta function. And so the idea is you have local information, you have what's going on at each prime, and you use this to build up a function. And what's remarkable is that this built-up function is very nice. And so the idea is maybe somehow by understanding sums of integers, we can use that to deduce information about the primes. So I'll start with two consequences. So we've got the Euler product. So these are special values. Okay, let's take the limit as s goes to 1 from above of zeta of s. This is the sum n goes from 1 to infinity of 1 over n to the s. So as s goes down to 1, this explodes. There must be infinitely many primes. If there were only finitely many primes, then since this is also equal to the product p over primes of 1 minus 1 over p to the s inverse, if there are only finitely many primes, this product would be finite for each s, and its limit would be finite. So as product is finite if finitely many primes must be infinitely many primes. So that's a wonderful result. There must be infinitely many primes. You can get some information if you want about how many primes there are. And so what we could do, and I'm going to just do a quick bullshit approximation. You can make this more precise, but this is a skill you need to learn if you're going to become a professional mathematician. How can you do rough ballpark estimates of what's going on? Get a sense of what the value is. How many primes do you think there are up to x? Give me a bound. It can be a bad bound. Has to be less than x. Technically, it has to be less than or equal to x, but then you very quickly realize, because 1 is not a prime. We do not let 1 count itself as a prime, but we don't let it count itself as a composite. We put it in a special category by itself as a unit. All right, so there's at most x minus 1 prime. Oh, there's at most x primes, because x might not even be an integer. Give me a lower bound on the number of primes. 1 or 0, depending on how large x is. Ballpark, it turns out that the number of primes up to x is about x over log x. So in the limit, since x over log x numbers are prime up to x, that means the percentage of numbers that are prime is about 1 over log x. So percentage-wise, the number of primes goes to 0. Are there more primes or more perfect squares? How many numbers up to x are perfect squares? So yeah, about square root of x. So pi of x is different than the product pi, is the number of prime of p less than or equal to x, p is prime. This is about x over log x. So density of primes up to x is approximately 1 over log x. Density of squares is approximately square root of x over x, or 1 over square root of x. So there's a lot more primes than perfect squares. If you looked at the sum of the reciprocals of the perfect squares, does it converge or diverge? The sum of 1 over n squared. Converges. And then, just to make your life completely miserable, when we do these convergence tests, what do you call these convergence tests in calculus or analysis? What kind of series do you call these? These are called p-series. The p is not supposed to be associated with the integer n. The p is supposed to be the prime on the other side. Okay? In Calc 3, you should be shot if you start introducing s and doing this as a complex, quantity. Right? You should not be doing complex numbers here. So we call it p-series, which is a little bit unfortunate when we get to complex analysis now. The sum of 1 over n squared converges. It turns out that the sum of the reciprocals of the primes diverge, which means there's a lot more primes than perfect squares. It's unknown if there are infinitely many twin primes that differ by 2. Through remarkable breakthroughs a couple of years ago, Liang Zhang showed that there were infinitely many primes that differed by something like 73 million. It was a phenomenal breakthrough. It was then winnowed down to, I think it's around somewhere between 200 and 600. I haven't checked the internet today to see just have there been any improvements. If you assume a couple of reasonable conjectures, I think they can push the methods down to 16. We don't know if there are infinitely many twin primes. We expect there are. We have predictions for how many there should be. Brun proved that the sum of the reciprocals of the twin primes converge. And I have a colloquium student who I think is going to give a talk on this. So if there are infinitely many twin primes, there's not enough of them to make the sum of the reciprocals converge. This is one of the few mathematical things my wife occasionally mentions in her marketing classes. So how many of you have ever seen a computer using an Intel chip? Right? Most chips are Intel chips. They used to call their chips the 286, the 386, the 486. And they decided to do a huge marketing campaign that it's the chip that really matters. And you want an Intel Pentium chip. And so a mathematician nicely was trying to calculate the sum of the reciprocals of the twin primes. And when he was doing this on a Pentium computer, the first couple of digits were good, but then they didn't match what he had done on a 486. And it turns out every couple of billion divisions, the Intel chip made a mistake. Now, most people are not going to have to divide billions of times very large numbers and add them. Intel knew about this but didn't really think it mattered. And so it became a terrible publicity where Intel's competitors go, we have to agree with Intel. The chip does matter. Ours can divide. And so there was this massive recall on Intel chips where frantic, worried customers could get a replacement chip that actually divides properly. Now again, for most people, you would never see any meaningful difference in what's going on. Maybe if you're aiming a ship to the moon, maybe something like that, you would care about that many digits down. For the most part, it didn't matter. But in terms of how much money Intel lost for this, it was huge. It's one of the nice examples of pure mathematics being useful as a way to just test and debug computers. Can you trust the output that's coming? You want to calculate anything on a computer, you want to calculate multiple ways. Computers have bugs. So the reason is, let's look roughly at what's going on. So the following is not justified, but it's not horrible. Let's look at the sum n less than or equal to x of 1 over n to the s. Maybe it's the sum of the product p less than or equal to x of 1 minus 1 over. Seem reasonable as a rough approximation. Let's take s equals 1. So the nice thing about being at the blackboard is I can just do that. Approximately, what is the sum of 1 over n from 1 to x? This is approximately, what's the harmonic sum?
1 over n minus 1.
No, this is diverging. It's going off to infinity, right? How quickly does the sum of 1 over n diverge? It's about log x. So the sum, 1 plus a half plus a third plus a fourth plus a fifth, it's about log x. One nice way to see this, 1 plus a half plus a third plus a fourth. Each of these is at least 1/4. So the sum of these terms is greater than a half. Each of these is at least 1/8. The sum of these terms is at least 1/2. This proves that they diverge, and it also gives you, roughly, if you play with it, a logarithmic divergence rate. And you can get upper bounds and lower bounds by doing this. So you can prove logarithmic divergence. We have a product on the right-hand side. What should you do when you see a product? Take the log. If you do not see a product and think log, I have failed you. Okay? Your default should be whenever you see a product, take a logarithm, unless you're in an elementary school trying to teach kids how to multiply. All right, so we want to take 3 times 4. So we take the log of 3, and we take the log of 4, and then we add them, and then we exponentiate. Can I have that student help me? Okay, that's probably the one time not to take a product. Other than that, take products when you see logs. So if we take logs of both sides, we get log of x is approximately, the log of a product is the sum of the logs. The negative 1 comes out. Negative sum p less than or equal to x log of 1 minus 1 over p. Well, the log of 1 minus u is approximately negative u up to lower order terms. So this is approximately the sum p less than or equal to x of 1 over p. And it turns out that this result is actually correct. The sum of the reciprocals of the primes is about log x. And if you think back to the sum n less than or equal to x of 1 over n, this is about log x, does it make sense that this is smaller, that this is smaller than this? Yeah, every term here is here, and this has a lot more terms because most numbers aren't prime. So there's still enough prime so that the sum of the reciprocals diverge. So you can make this more accurate, and you can use this to get a statement that the sum of the reciprocals of the primes diverge, and you can try to work and get what's the right growth rate. It's slow. You know, if you thought log x was slowly growing, look at log x. Okay, the last special value thing I want to say about the primes is we looked at what happens as s goes to 1. Let's look at what happens as s goes to 2. When I take s equals 2, I get the sum n goes from 1 to infinity of 1 over n squared is the product over all primes of 1 minus 1 over p squared inverse. Well, anybody know what the sum of 1 over n squared is? It's a famous sum. Pi squared over 6. This is the same as the product. This is p squared minus 1 over p squared. Take the reciprocal. It's p squared over p squared minus 1. If there are only finitely many primes, this is rational. Pi squared is irrational. So because pi squared is irrational, there must be infinitely many primes. This is, we've talked about tactical nuclear strikes on mathematics. This just seems either beautiful or wrong, depending on your point of view. I really don't think there's an intermediate. You've got to either absolutely love the elegance of this or just be frustrated at the overkill that's being done. The other thing is, at first, it looks like a very strange result where we have no idea about how many primes there are. It just tells us that there must be infinitely many. If there weren't infinitely many, there'd be a problem. Well, how many primes are there up to x? It's not clear from this. So how many of you have seen Euclid's proof of the infinitude of primes? Has anybody not seen Euclid's proof? Okay. So Euclid's proof, the copyright has expired. It is probably one of the most used proofs in all of mathematics. So Euclid's proof that pi of x goes to infinity. So assume there are only finitely many primes. So you can look at p1 times p2 times the last prime and add 1. Either this number is prime and you have a new prime on your list, or it's composite. Can p1 divide? No, remainder 1. Can p2 divide? No, remainder 1. Can p3 divide? No, remainder 1. So either prime or divisible by prime not on list. Thus, list not complete. So in either case, you find that there's a new prime. Now, what's interesting about this is you can get a growth rate from this. And you get a growth rate like log x. The number of primes up to x is like log x. The growth rate sucks. It's nowhere near x over log x. But at least it goes to infinity and you can make it explicit. So a couple of years ago when I was a postdoc, I was wondering, could you somehow make this explicit and get an estimate on how quickly the primes are growing? And I was able to prove, I think, like log x, which is worse than Euclid. And then I found out that not only was my result worse than Euclid, but I was using what's called the irrationality exponent of pi squared, which involved using the prime number theorem. So by assuming that the number of primes up to x is x over log x, after a lot of work, I was able to prove that there's at least log x primes up to x. There are faster ways to prove this. So what I then did is I then actually opened up the argument, and I'll post the paper, where we looked at, well, where is the prime number theorem used to prove this? And so at the end of the day, we were actually able to get a nice result, and this was finally finished up with some Williams students a few years ago, of almost x over log x numbers of prime up to x infinitely often. And so I'll show that you can get growth rates from this. It's a little bit hard, but you can make it work. There's a topological proof on the infinitude of primes. using open and closed sets, which has no chance of getting anything explicit. So it is by Hillel Furstenberg. How many of you know about Erdős numbers? Okay, so did you know Erdős numbers? No. Okay, so Paul Erdős wrote over 1,000 papers with over, I think, 500 contributors. So you have an Erdős number of 1 if you wrote a paper with him. If you wrote a paper with somebody who wrote a paper with Erdős, like myself, my Erdős number is 2. My kids have an Erdős number of 3 because they wrote a paper with me. And then there are other things. There's the handshake number. You know, how many handshakes do you need before you get back to Gauss or Riemann? There's also the drinking number. Have you had a drink with somebody who's had a drink with? So my Furstenberg drinking number is 1 because I knew one of his thesis students, Vitaly Bergelson, who is a big professor at Ohio State. And so when Furstenberg came to visit, I was there and got to meet him. So fascinating, fascinating result. I will post this. You should know these different proofs because you're now getting to the point in your careers where different proofs give you different perspectives. You know, it's nice that we have a day like this. We can talk, think, look at how these things connect. I mean, there's a lot of stuff going on here. You can try to generalize this to other sequences. You know, what about primes in arithmetic progression? You can prove that there are infinitely many primes congruent to 3 mod 4, but not 1 mod 4. And I'll leave that as something to think. But there's something that most people have not seen about this Euclid sequence. Let's start off with the first prime. What's the first prime? 2. This is not a hard question, people, okay? Let's apply Euclid. 2 plus 1 is 3, is 3 prime. Add it to the list. 2 times 3 is 6. Add 1, 7 is 7 prime. Whoa! Anybody want to make a conjecture? We have 3 data points. You want a 4th data point? Fine. 2 times 3 times 7 is? Add 1. All right, does anybody want to now make a conjecture about the Euclid sequence as to... Oh, come on, guys. You don't trust me? All right. Well, what is 2 times 3 times 7? We know what that is, right? It's got to be 1 less than this number. So 42 times 43 plus 1. So we get 1,807. What do you think, prime or not prime? Any thoughts? Nice to be at the blackboard with Mathematica. 13 times 139. So it does not always return primes. So there's a couple of ways you can play the game. One way is you could put in now all the primes that divide the number, or you could just put in the smallest prime. And then you can ask, as you iterate, will every prime be generated? And if so, how long does it take to get to certain numbers? There is very little known about this sequence. The reason is the numbers explode so rapidly, it becomes a computational nightmare to deal with these. But it's nice because this is a sequence, hopefully, or this is an idea many of you have seen before, but the idea of trying to make this explicit, trying to get some idea of the growth rate, that's a little bit novel. And then as a good exercise, try to show there are infinitely many primes congruent to 3 mod 4. See if you can generalize this argument. There's a nice paper by Ram Murty, and I think one of his colleagues, I can't remember who, about for which arithmetic progressions can you prove that they're infinitely many by some kind of trick like this. And Ram Murty is actually how I have my Erdős number of 2 from writing a paper with him. In general, the only way we know how to prove that there is even 1 prime in an arithmetic progression, let's assume the arithmetic progression is not stupid. If your arithmetic progression is 3n plus 15, 3 and 15 are both divisible by 3, all your numbers will be divisible by 3. So let's assume you have an arithmetic progression an plus b, where a and b are relatively prime. In general, the only way we know how to prove that there's even 1 prime in an arithmetic progression is to prove that not only are there infinitely many primes in that arithmetic progression, but that the number of primes in that arithmetic progression is basically the same to the first order no matter what b is. The primes fall evenly among all the different classes, therefore there's at least one. This goes back to the tactical nuclear strike and the overkill. The only way we know how in general to prove that there's one is to prove that there are infinitely many. All right. So now, let's look at the zeta function. So zeta of s is 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s plus 1 over 5 to the s plus dot dot dot. I'm going to multiply by 2 over 2 to the s. And I'm going to subtract. So 1 times 2 over 2 to the s is I'll have a negative 2 over 2 to the s. And then when I multiply this, I'll get a 2 over 4 to the s. And the next one is I'll get a 2 over 6 to the s. So now, let's do the subtraction. We get 1 minus, 2 over 2 to the s is just 2 to the 1 minus s times zeta of s is equal to 1 minus 1 over 2 to the s plus 1 over 3 to the s minus 1 over 4 to the s plus 1 over 5 to the s minus 1 over 6 to the s. So we can write this as a sum and goes from 1 to infinity of, we'll call it eta of n over n to the, well, if I write eta, it's probably going to be hard and confusing. I'll write g. So g of n is equal to 1 if n is odd and negative 1 if n is even. And in fact, I can then say zeta of s is 1 over 1 minus 2 to the 1 minus s. So this is another way of writing the zeta function. The zeta function as originally written only exists if the real part of s is greater than 1. What we want to do is we want to try to extend this to a function for all values of s. This is the cheapest, easiest way to extend it. It's not the best extension. Does this remind you of anything? It's an alternating series. But the problem is we have this factor of s. So s could be complex. So it may not stay alternating. How might we want to handle the sum of g of n over n to the s? What tool might we want to use? Partial summation. Right? Let's look at the sum, n goes from 1 to big N, of g of n, h of n, where h of n is n to the negative s, so h prime of n is going to be negative s, n to the negative s plus 1. So notice that h of n is decaying, and h prime is decaying even faster. So this goes back to why we care so much about partial summation. For us now, I'll call it, g of x is going to be the sum n less than or equal to x of g of n. What can you tell me about the possible values of g of x? It's either 1 or 0. So we know that g of x is either 1 or 0. That's the whole point. Even though, unfortunately, that s could cause us trouble, because the g of n is so nicely alternating, we can use that to get cancellation. And so now, when we go through and try to figure out what is that sum equal to, well, now using partial summation, we get that this is equal to, g of n h of n minus the integral from 1 to n of g of x over n to the s plus 1, and the negative sign makes that a positive. Now, take the limit as n goes to infinity. Well, what does g of n, h of n go to? So what will g of n, h of n go to? If you want, I can write this as goes to 0. And in fact, it goes to 0 as long as s is greater than 0 for real part. We don't need s greater than 1 for real part. And now over here, when will this integral make sense? Well, as long as the real part of s is greater than 0, this integral makes sense now. We have enough decay. And so we get zeta of s is equal to 1 over 1 minus 2 to the 1 minus s, integral from 1 to infinity, g of x, n to the s plus 1 dx. This integral here is okay if the real part of s is greater than 0. So later we will get a better analytic continuation of the Riemann zeta function. But for now, this is a pretty good one. What about this factor 1 over 1 minus 2 to the 1 minus s? Where is that bad? So the only place where this is bad is s equals 1. This is actually beautiful at s equals 1. This is like a sum of 1 over n squared. Beautiful. So the question is, how bad? So what does 1 over 1 minus 2 to the 1 minus s look like near s equals 1? I'm sorry? It looks like massive. This is going towards 0. But we want to quantify. We want to do an expansion of this. And so let's now beat the clock. So we want to look at 1 over 1 minus 2 to the 1 minus s. This is equal to 1 over 1 minus e to the 1 minus s log 2. Never, ever work in any base other than e. Okay? Well, how do I study this? This is equal to 1 over 1 minus, now I just do the series expansion for e. So I'll get 1 plus 1 minus s log 2 plus 1 minus s squared log squared 2 over 2 factorial plus dot dot dot. The ones cancel. I can pull out a 1 over s log 2. I get 1 over 1 minus s, 1 over log 2. And what I'm left with is 1 over, these cancel. I guess there's a negative sign that comes from this. So I'll pull out the negative sign as well. Oh, and the negative sign now allows me to write this as s minus 1. And now I will have, I pull this out, I'll have a 1 plus 1 minus s log squared 2 over 2 factorial plus 1 minus s squared, I think, log cubed 2 over 3 factorial. But as s goes to 1, this term here goes to just 1. So this is basically going to like 1 over log 2. So it's looking like this has a pole, a simple pole. Now, I've got to somehow figure out what this is. And because it's a simple pole with residue 1, somehow this has to get me a log of 2. So I'll leave that as an exercise of trying to get a log of 2 from this. But this is meant to be an introduction to the Riemann zeta function and to counting. We have not gone into the gamma function. You should be able to figure out what we'll be doing on Friday. We will do the gamma function. And a better analytic continuation involves the gamma function. Yes?
Did you already pull out the log?
Oh, yes, you're right. I did. So these should be, you're right, these should be all the same powers. Thank you. So those should be both that, and then this should be squared. Thank you. You're right. Yes. I will admit I don't really care what's going on past the 1, and I'm not giving it the attention it deserves. All right, so we did a lot of good stuff today. And so